Hello, friends, and welcome to yet another lecture on chemical engineering thermodynamics. I am going to make a slight change in my presentation pattern. Now, from now onwards, I'll be speaking more in a style as if I am talking in a classroom. So, rather than being very brief, I'll be elaborate on each and every slide. On every slide, we'll be spending more time. It will be speaking will be a lot slower, a lot more explanatory, and let's see how does it work. Now today's topic is going to be reaction equilibria. I am Professor Arvind Prasad. I assume that most of you who are watching this lecture have no background on thermodynamics and may not have a background in properties of mixtures in thermodynamics. But you have some background of calculus. So, assuming that that background is there, I'll start with the elaborations. Let's assume that we are mixing two pure fluids, M1 and M2. We are mixing them in a beaker. As you can see that the beaker is open to atmosphere. These two fluids too are open to the atmosphere. And it's but natural to assume that the temperature of M1 and M2 are equal, and it is equal to the atmospheric temperature. And we also assume that when we mix, the temperature of the mixture M is also constant. Now, it may not be equal to the atmospheric temperature. It may be equal to the atmospheric temperature. Well, if we mix M1 and M2 and get M, and there is no heat of mixing or heat of solution. What is heat of mixing, heat of solution? Well, when you mix two fluids, sometimes heat is generated. Sometimes heat is taken. So whenever heat is generated, the solutions get heated up. And whenever the solutions are mixed and heat is taken away from the solution, normally the solution cools. Therefore, we have an exothermic mixing where heat is generated, and we have an endothermic mixing where heat is consumed or heat is taken. Now, it may happen that when we are mixing this, the heat is being generated or the heat is generated. But all said and done, the temperature is constant. In that case, if M is a property, now what do we call a property in thermodynamics? There are state variables in thermodynamics, which are pressure, temperature, volume. We call them state variables because they determine the state of the fluid. We all know that at a certain temperature and pressure, water will be a liquid. At some other temperature and pressure, it will be a gas. Therefore, these variables, that is temperature and pressure, they determine the state of water. And they are known as the state variables. Volume also is a state variable because volume shows whether it's a liquid or it's a gas. The other state variables in thermodynamics, without much elaboration, are going to be internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Usually these terms that is enthalpy, Gibbs free energy, Helmholtz free energy, they are mathematically introduced to ease out calculations. Internal energy is something you can relate to in physics, right? It's sum total of all the energies that the molecules have. Enthalpy is nothing but the internal energy added to the pressure into volume of the mixture. And Gibbs free energy and Helmholtz free energy have their respective definitions. Well, if I take any property, now the property in this case I'm referring to will mean either internal energy, enthalpy, entropy, Gibbs free energy, or Helmholtz free energy. It would mean any of these. If the property of this mixture M depends on temperature, pressure, N1, N2, so forth till Ni. And yes, for this mixture, let's say internal energy depends on temperature, depends on pressure, and also depends on the relative concentrations of species 1, 2, 3, 4, 5, 6, whatever the species are there in this mixture, it depends on their relative quantities. Now, the internal energy of this mixture can be changed by changing the temperature. It can also be changed by changing the pressure. But one should also understand that I can change the internal energy of this system because it's an open system. I can add mass to it. I can change the total amount of internal energy in this by adding quantities to this or by adding mass to this. Therefore, the change in property of this system is equal to the change in property of the system with respect to the temperature, which is written by the first term in the differential equation. Change in property of the system with respect to change in pressure, which is represented by the second term in this equation, and sum of all the changes to this property by addition of all the species into this mixture. Here I have shown 2, but we may add more. The last term is nothing but change in property of the system to addition of moles to the system at constant temperature, pressure, holding Nj constant. Now what does this mean? Supposing I stop the addition of 2 and start the addition of 1. This quantity would become dou Nm by dou N1 Tpn2 dN1. So the summation for all such additions, the first one obviously is going to be the change in property of this system for addition of N1. The second one in this summation would be the change in property of the system for small addition of 2, so on and so forth. Now, the last term, this has a special name. It's known as partial molar property. The partial molar property of any species I in a mixture is nothing but the change in property of the mixture to addition of I to that mixture into dNi. So we can say what we have put mathematically in simple language. The partial molar property of a species I in a mixture is the change in the total property of the mixture to small addition of that species. Now, Gibbs free energy of this mixture is going to be a function of temperature, pressure, and the number of moles or the amount of moles of each species in the mixture. Like the previous equation, which was this, we can write dNg is equal to, or the change in Gibbs free energy of the mixture is equal to change in Gibbs free energy of the mixture to change in temperature. That's by the first term. Change in Gibbs free energy of the mixture to change in pressure. That's the second term. And summation of the change in Gibbs free energy to addition of any species, holding the other species constant at constant temperature and pressure. Therefore, the partial Gibbs free energy of any species I in the mixture is nothing but change in Gibbs free energy of the mixture to a small addition of that species at constant temperature, pressure, and holding the other species constant, not adding them. G bar I is nothing but a partial molar property, or it's the partial molar Gibbs free energy. Therefore, we can write dNg is equal to dou Ng by dou T into dt, dou Ng by dou P into dP, holding T constant, plus summation of Gi bar dNi. What we do is we just replace this in this equation with Gi bar, and we get this here. Now, for real gases, now we will talk about only mixtures which are nothing but gases. For real gases at constant temperature and pressure, the equation that we have here just comes down to this. Why? Because if the temperature is held constant, the first term is 0, pressure is held constant, the second term is 0, and we are left with nothing but dNg on the LHS and summation of Gi bar dNi on the RHS. So we can write this, that change in property or change in Gibbs free energy of the mixture at constant temperature and pressure is only equal to nothing but the summation of the partial molar properties of the species in the mixture to their small additions. Now, let's focus our attention on what would happen if the moles changed because of reaction. Now, moles in a mixture can change because we are adding moles to them. But moles in a mixture can also change because a reaction occurs in them. It may be a closed system. We may start initially with some amount of moles of reactants A and B, and we might end up getting a mixture finally of A, B, C, and D, where C and D are the products. Nevertheless, to start with, we had a mixture, and to end with, we have a mixture. Now, the change in Gibbs free energy of such a system which is undergoing a reaction, dNg at constant temperature and pressure, is equal to nothing but summation I Gi bar. But in this case, we write it the partial Gibbs free energy of formation. We take this quantity as the Gibbs free energy of formation. And dNi is replaced by nu I d epsilon, where epsilon is nothing but the extent of reaction. For a closed system, at constant temperature and pressure at equilibrium. What is a reaction equilibrium? At reaction equilibrium, when any reaction reaches equilibrium, when N2 and H2, for example, form ammonia, N2 and H2 are never completely reacted to give you complete amounts of ammonia. There's always going to be an equilibrium. Whenever we put nitrogen and hydrogen and we put it in a beaker and create the right conditions, we will get ammonia. But nitrogen and hydrogen will never be completely consumed to give you ammonia. So we are going to have an equilibrium. Now this equilibrium is a function of temperature and pressure. But at equilibrium, what do we find? That the nitrogen, hydrogen and ammonia, their concentrations in the reaction mixture do not change. To start with, nitrogen and hydrogen are getting consumed. Their concentration change. But at equilibrium, the amount of ammonia in that beaker or round bottom flask and the amount of nitrogen and hydrogen, it all remains constant. If that remains constant, the extent of reaction is 0 at that point of time. Therefore, at equilibrium, we say that the change in Gibbs free energy of that mixture at constant temperature pressure is nothing but 0. Now, for real gases also we can write that the partial Gibbs free energy of any species in a mixture is nothing but the Gibbs free energy of that species at 1 atmosphere pressure, but the temperature at which the mixture is, Gi is nothing but partial Gibbs free energy of species I at the temperature and pressure of the mixture. Gi0 is nothing but the pure species of I, its Gibbs free energy at the temperature of the mixture, but at 1 atmosphere pressure. This needs to be noted. Plus RT ln of Fi cap, where Fi cap is nothing but the fugacity of the species I in the mixture. It's not the pure species fugacity, but it's fugacity of the species I in the mixture. Therefore, for a reacting mixture, we can write, we just multiply this by nu I and we get nu I GiF0, right? We write this as F because now Gi here, okay? As we go back, we can see Gi here was replaced by GIF, that is the Gibbs free energy of formation. Okay, so naturally we get here GIF, that is Gibbs free energy of species I, pure species I, the Gibbs free energy of formation of pure species I at 1 atmospheric pressure multiplied by its stoichiometric coefficient plus RT. Now if nu I was multiplied to ln Fi, we can always take nu I on the superscript, or we can always raise it to nu I. So therefore we have nu I or Fi raised to nu I, ln Fi raised to nu I. This is equal to 0. Rearranging the equations, that is taking this on the RHS and leaving this on the LHS, we get minus summation nu I GIF0 is equal to RT ln of product Fi nu I. Now what does this products mean? If we have species 1, 2, 3, 4, this symbol represents we will be doing an mathematical operation of F1 cap, that is the partial fugacity of species 1 raised to its stoichiometric coefficient, that is nu1, multiplied by F2 cap nu 2 multiplied by F3 cap nu 3 multiplied by F4 cap nu 4. Now for real gases, we can replace Fi with phi I cap Yi into P, where Yi is nothing but the mole fraction of the species I in the gaseous reacting mixture. P is the pressure of the reacting mixture, and phi I bar is nothing but the fugacity coefficient of the species I. Now, if it's a cap, obviously it's the fugacity coefficient of species I in the mixture, not the pure fugacity coefficient. We write pi phi I yi p raised to nu I as k, where k is the equilibrium constant for the reaction. K is equal to product phi I cap yi p raised to nu I. We should always note that the equilibrium constant K is only a function of temperature. Remember this, K is only a function of temperature. It's very difficult to understand this, and many people have a lot of misconceptions about it, that the equilibrium constant is a function of temperature and pressure. But I wish to make this very clear that it's a function of temperature, and I will prove it to you that how is it so. Now concentrate on the equation here. ln k is a number. Now on the LHS you have summation nu I GIF 0, where 0 indicates that this is the Gibbs free energy of formation of the species I at a pressure of 1 atmosphere and the temperature of the reaction. And of course, at the denominator you have the universal gas constant R and the temperature of the reaction. So this makes K only a function of the temperature. Another critical understanding. Yes, fugacity does have the dimensions of pressure. But in this equation, we need to understand here that with every fugacity, implicit is a division with 1 atmosphere. Therefore, here it is nothing but Fi divided by 1 atmosphere, the whole raised to nu I. Therefore, each and every term which is a fugacity and which is divided by 1 atmosphere, therefore is dimensionless. And that makes K dimensionless. Now for ideal gases, we can say that nu I cap is equal to 1. That is, the partial fugacity coefficient is 1. Therefore, we can write K as products xip nu I, where xip is nothing but the partial pressure of the species I in the reaction mixture. Now let's see that whatever we have done or whatever we have derived, does it predict similar to the Le Chatelier's principle? Now let's first understand what is the Le Chatelier's principle. Well, Le Chatelier's principle for reactions in equilibrium says that when any system at equilibrium, that is a reacting system at equilibrium, for a long period of time. Now for a long period of time was added because you need to understand one thing. It is for systems which are in equilibrium and truly in equilibrium. For a long period of time would mean that there are no changes in the concentrations of the reacting mixture for a long period of time, is subjected to a change in concentration, temperature, volume or pressure. The system changes to a new equilibrium, and this change partly counteracts the applied change. Now let's really try and understand this. Let's take the example of temperature. We know that summation nu I gi f 0 is equal to minus RT ln K. Now Gibbs free energy is nothing but the enthalpy minus the temperature into entropy. Now if we neglect the entropy of reaction, we can write the LHS as summation nu I hi f 0, which is nothing but delta H R, that is the heat of reaction at temperature T but pressure 1 atmosphere. This is equal to minus RT ln of K, or we can write RT ln of K is equal to minus delta HR over RT. Now, for small changes in temperature, as we have noted, the heat of reaction is negligible. Well, I said the entropy of reaction was negligible, but now we assume here also that the heat of reaction for small changes of temperature is negligible. And this is true because for small changes in temperature, the only part for the heat of reaction which actually changes is the summation of the CPs, that is the specific heats, and the change in temperature. Now for small change in temperature, obviously the change in temperature being negligible and being multiplied by Cp, this change is going to be really very negligible. Now we may assume for this that the heat of reaction is constant for small changes in temperature. Therefore, now if we increase the temperature in this reaction, and if it is an exothermic reaction, if we take the example of an exothermic reaction, so for an exothermic reaction, delta HR is negative, and minus a negative number for delta HR or into a minus becomes positive. This entire quantity on the numerator becomes a positive number. A positive number divided by R gives you a positive number. Now ln K is equal to a positive number divided by T. So ln K is inversely proportional to temperature for an exothermic reaction. So therefore it is but natural that for an exothermic reaction, increase in temperature will reduce the value of K. And reduction in the value of K means the reaction equilibrium has shifted towards the reactants. Now K, as stated earlier, is nothing but the product of the partial pressure of the products over the product of the partial pressure of the reactants raised to their stoichiometric coefficients. Now if K reduces, it's but natural the partial pressure of the products will reduce. And therefore, if we increase the temperature for an exothermic reaction, the equilibrium shifts towards the reactants. The converse is also true. If we decrease the temperature, this will increase the value of K for an exothermic reaction, or this will shift the reaction towards the products. Now let's take the pressure effects for the reaction. K is nothing but products, partial pressures raised to the stoichiometric coefficient. Or we can write it as a product of the concentrations or the mole fractions multiplied by the pressure raised to the summation of the stoichiometric coefficients. Now, for a reaction whose volume does not change, which means a reaction for which the total number of moles initially is equal to the total number of moles finally. Nu I will be equal to 0. Therefore, pressure will have no effect on product of the concentrations raised to their stoichiometric coefficients. And therefore, the reaction equilibrium will not shift. But for a reaction whose volume has increased, that is, summation nu I is greater than 0, that is, the stoichiometric summation of the stoichiometric coefficients is greater than 0. Now let's assume you have a reaction which is 1A plus 1B giving you 3C. The volumes here have increased. You had one volume of A and one volume of B giving you 3 volumes of C. And therefore the change in stoichiometric coefficients is nothing but 3 minus 1, that is 1. Increasing the pressure will reduce the product of Xi raised to nu I. Why? Because K is constant, the temperature is fixed. It's but natural if we increase the pressure, this product has to reduce. And if this product has to reduce means the partial pressure of the products have to reduce. And therefore the reaction shifts towards the reactants. The converse is also true for a reaction whose volume increases, that is summation nu I. Beg your pardon, I need to make a small change here. Yes, for a reaction whose volume decreases or summation nu I is less than 0, increasing the pressure will increase the value of this, that is nothing but the product of concentrations or mole fractions raised to their stoichiometric coefficients. Therefore, the reaction will shift towards the products. Now, let's take an example. For an ammonia synthesis reaction, we write K as partial pressure of ammonia over the partial pressure of nitrogen raised to 1 by 2. That is nothing but the stoichiometric number of nitrogen, and partial pressure of hydrogen raised to 3 by 2. That is nothing but the stoichiometric coefficient of hydrogen in the reaction. The value of K as a function of temperature is here. Let's find out what is the conversion at 100 bar and 370 degrees Celsius. For every 1 mole of nitrogen, there are 3 moles of hydrogen which enter the reactor. That is the ratio which is maintained in an ammonia reactor. Now the value of K at temperature 643 Kelvin is 0.02144. This has been calculated by replacing 370 degrees Celsius as Kelvin, which is nothing but 643, in this expression. Therefore, we have K is equal to this expression, where this is nothing but the pressure raised to the summation of the stoichiometric coefficients of the reaction, which is nothing but minus 1. Now on the top we have the mole fractions of ammonia. Now if X amount of ammonia is, or X moles of ammonia is formed, The mole fraction of ammonia at the exit of the reactor or at equilibrium is nothing but X over 4 minus X. Now, how do we arrive at 4 minus X? Well, let's note, to start with, we had 1 mole of nitrogen. If X moles of ammonia are produced, the amount of nitrogen consumed is X by 2. If 3 moles of hydrogen are fed, the amount of hydrogen consumed are 3 by 2 X. Therefore, X is the amount of ammonia. 1 minus X by 2 is the amount of nitrogen at equilibrium. And 3 minus 3 by 2X is the amount of hydrogen at equilibrium. Adding X to 1 minus X by 2 and adding that to 3 minus 3 by 2X gives you 4 minus X. Therefore, 4 minus X is the total number of moles at equilibrium. Individual moles, that is X for ammonia, divided by the total number of moles is nothing but the mole fraction. The similar reasoning goes for mole fractions of nitrogen and hydrogen. Noted, we have already calculated the value of K. Now, on the LHS, we have 0.02144 into 100, and on the RHS, we have the expression for X. Now, there's a suggestion here. For those who want to solve it on a calculator, it would be really worthwhile that you simplify this expression. You get a order 4 polynomial and solve the order 4 polynomial on the calculator, and you get your answer. You could also use tools like WX Maxima and get the answer. The value of X is 0.97211. Now, please put on the comments how much is the conversion. You would be surprised to know the value of the conversion. It is pretty high. But then we forgot something here. Thermodynamics allows us in calculating the equilibrium of a reaction. It never tells us how fast or how quickly are we going to achieve it. It would be worth noting that as the reaction reaches the equilibrium, the rate of reaction falls, and it falls drastically. Therefore, reaching the equilibrium value requires a very long time. The time that the fluids spent in the reactor is limited. Therefore, a compromise is made in most of the reactors between the time the fluid spends in the reactor and the equilibrium conversion one might get. This is an economic exercise and an engineering exercise too, because a lot depends on the engineering of the reactor also. That was the end of my lecture. Hope you enjoyed it. I hope the professionals in chemical engineering also enjoyed it watching this video. For students, this would have been a real worthwhile exercise, because this is an important topic in chemical engineering thermodynamics. Please subscribe and like my video, and do watch my entire playlist on chemical thermodynamics. Have a great evening. Have a good day. Bye.